Good morning, everybody. We're going to have some fun this morning. I always like to have fun up here, and you gave me such a large stage, I have to use it. My paparazzi, everyone. Okay, this is going to be a talk that developed from an experience I had working on a Go service that we had to run in Kubernetes, and it was the first time I was using Kubernetes. Now, before we get deep into the talk, I want to get a system up and running. No magic. I've got nothing going on here right now. So I'm going to bring up a local Kubernetes cluster. I'm going to be using a technology called KIND, K-I-N-D, which in English stands for Kubernetes in Docker. I love KIND. And the talk itself, it doesn't matter what you're using to run Kubernetes in, but that's what I'll be using. My Docker right now is set up to use all 12 cores that are on this M2 with a bunch of memory. I'm not going to go deep into the Kubernetes side of clusters and things like that, but let's just at least get that system up. So I've got a few make commands, and this is how I work pretty much every day. So I'm going to do a make talk up. That's going to bring up our Kubernetes cluster. And on this bottom screen, I'm going to run a command that will sort of give us the status of the cluster as it goes. Now, normally I would make this smaller so we can see everything, but this is a very large room. So I'm just waiting right now for the 9 services to come up so we can then do the next stage here and I'm going to make this just a tiny bit smaller so I can at least see what's going on here. So once I get the cluster up, I've got 3 binaries or 3 different services that we're going to be running with this. Okay, so the cluster's now up. If I do Docker images, you'll see at the top of the list a auth service, a sales service, a metric service. We're going to run this in the Kubernetes cluster, and I'm going to be running a Postgres database. All this code that I'm running comes from the Ultimate Service class that I've been teaching with the workshops. So now that we've got that, everything's already been built. I'm going to do a make talk load. What this is going to do is take those local images and load them up so KIND can find them. And then I'm going to do a make talk apply, which will apply some YAML that we have to get those 2 pods that I need running, one for the sales and one for auth. Now, once that's done, we'll just test to make sure that the sales API is up and running, and we can hit it, and then we can start talking about our story here. But I'm trying to make sure that you see this is all live, no fun and games. Everything is, though, running locally. All right, so we're just waiting for the remaining thing here. So I'm going to make this just a tiny bit smaller for myself at this point. If you sat in the front, great. All right, and I just want to see, for those in the back, you're not going to see it. I just needed to see that the sales pod is running 2 of 2 services. So I can now just test it. I'm going to need a token. So that's going to make a get call to the service running in Kubernetes. I have a JSON web token here. I'm going to save that token in a variable. And I'm just going to make sure that I can actually it's talk. Actually, let's do this. Make dev, should have been, users, sorry. All right, so when the system came up, it put 2 users in the system, and this was a simple curl call that's hitting the service that's running in the sales pod to access that. All right, so just a curl call with the token. Okay, perfect. So here I am. I've got a service that's running. It's in Kubernetes. I can hit it. I can get a couple of users. So I have this system deployed at a customer staging environment. I'm really brand new to Kubernetes. I'm brand new to running things in there. The ops team has decided to use Argo CD. If you don't know this already, I hate ops. And I say, I need to see the logs. And they're like, oh, just go in Argo CD. And I'm like, yeah, just go in Argo CD. So I start poking around in Argo CD, but I'm deathly afraid because I don't want to like break something. Because I've done that in the past. It's not fun. And I'm trying to find the logs, and I come across some YAML that's being used to deploy the service that I'm writing. And this is what I see in the YAML. I see CPU limit 250M. Now, I know very little at this point what that means. I mean, if you read documentation, it says that you're getting 25% of a CPU, but like, what does that mean anyway? All I'm thinking is the ops team is starving my Go service, and I don't want to be starved. But no problem. I reach out to the ops team, and I say, why are you setting this? What does this mean? And they said the absolute worst thing they could have said. Bill, I don't know what that means. Google sets it. We don't touch it. Everything works. I'm like, wait, Bill, let me say this again. We're using managed Kubernetes on Google Cloud. They set this. We don't touch it. Everything works. That's my answer. Now, if any of you know me, that's not acceptable. So I go on basically a 2 to 3 day quest to figure out what this means and what's going on. And luckily, I have a few friends who are really, really good with the Kubernetes. So I'm asking everybody that I can get in touch with. So I'm going to share with you what I learned during that discovery. And also, what I learned, which is there are a lot of Go services running in Kubernetes that are not running as efficiently as they otherwise could when this setting is being used. So let's first talk about what this number means. Now, to do that, I'm going to set up a little whiteboard here. Let me just create a file. My favorite plugin ever, the whiteboard. And let's start to understand what this number means. So, as I initially said, 250M, where the M means millicores, that's the unit, represents that you want to use 25% of a given CPU. So if that number was 500M, 50%, 1000M, 100%, and you can use a decimal point if you wanted to, but somebody went out of their way to create this millicore unit. It's going to use it. Now, that still doesn't mean anything. What's 25% of a CPU? It's not like we can cut these things in quarters. And so then I learned that the following semantics take place. Do not worry about how this is implemented. It's not important. Implementations can change depending on versions and hardware and operating systems, so that's not important. What's important is the behavior I'm going to share with you. So, semantically, this is what's going to happen. And we're going to start simple. Let's pretend right now that the machine that's running Kubernetes, like this one machine, doesn't have 12 of these, it just has one. We can always talk in simple terms most of the time, as long as the behavior is consistent. We can go down, my friends here love the word rabbit hole. We can go down the rabbit hole. Maybe we'll go down a tiny bit, but let's start simple. So Kubernetes is going to start a 100 millisecond time cycle. So imagine that this clock starts, and in our simple world right now, for a single CPU. So every 100 milliseconds, what's going to happen is Kubernetes, in conjunction with your operating system, is going to look at what services need to run within the scope of that 100 milliseconds. Now, I said my service needs 25%. So really what I'm asking Kubernetes is for every 100 millisecond time cycle, you give my service, we'll just call it service A for now, 25 milliseconds. And then on the next cycle, guarantee me 25 milliseconds. And on the next cycle, guarantee me 25 milliseconds. That's 25% of each cycle. That's kind of interesting if I can do that, because remember a couple things here. Cloud computing's expensive, and so if we can share even a single CPU, maybe with 4 services, I won't need a lot more compute as long as it's fast enough. So now that gets interesting, fast enough. 25 milliseconds doesn't seem like a lot of time, does it? Time is hard. So we're going to come up with an average, we're going to come up with something that lets us understand time. So let's imagine on this CPU, let's imagine that it's running at 3 gigahertz. That's the clock. Now, on a machine with 1 node, we probably could average 3 gigahertz. On all these machines where it's multi-core, it tends to run maybe at 2.5. Obviously, they can spike and go down, but we only have to talk about averages. So let's just say, to keep it simple, we're running at 3 gigahertz at an average. What does that mean? What that means is that we're going to get 3 clock cycles, right? 3 clock cycles every nanosecond of time that goes by. That's what that means. Clock goes. And remember that nothing can happen on the machine without a clock cycle. The clock cycle is pushing those electrons through the machine. I always say I don't care how many layers of abstraction you have above the hardware. At the end of the day, a clock cycle has to happen for anything else to happen on the computer. Now, thanks to the magic of compilers and hardware, like things like pipelining, all this stuff you can go down the rabbit hole and look up. Thanks to the magic of all of that, we should be able to execute 4 instructions for every clock cycle, which essentially means the magic number that I want, okay, is essentially that every nanosecond that goes by represents 12 instructions on average. 12 instructions you executed, or 12 instructions you didn't. So if I said to you, you had a nanosecond of latency, what I'm really saying is there were 12 instructions that you didn't execute that you otherwise could have, but you didn't because you had to wait. Now, let's take this number and sort of look at it from an industry standpoint. Here's some industry-defined latencies, and that middle column is time. And if we use our 12 instruction per nanosecond as a way of really visualizing it, you start to see the number of instructions that you're losing. Look at a main memory reference, which costs you 100 nanoseconds. That's 1,200 instructions. You can do a lot of work in 1,200 instructions. So every time you have a cache miss and you got to go back out to main memory, that's honestly expensive. But I think my favorite one is the round trip within the data center, which is what we do every time we access our database. Every time we access our database, we could see easily a half a millisecond of latency on that. That's 6 million instructions. Now, this is why concurrency is so important. Because if we didn't have the ability to do something else while something was waiting, no work would ever get done. That's 6 million instructions that we didn't execute that we otherwise could. The funny thing about writing services that sit on the network is that your service is probably bored more than it's busy. It's probably waiting more than it's actually doing anything. And so when you hear me say things like, if you can pay for garbage collection, use Go, what I'm saying is, if you have a lot of this type of latency already built into what you're doing, and anything on the network has that, then there are free cycles available to you to do garbage collection. They're there. You're not using them because most likely you're waiting for something anyway. Go is really brilliant in this way, in its ability to try to allow you to leverage the full breadth of a CPU, the full breadth of memory. So now if I told you I'm going to give you 25 milliseconds of execution time every 100, do you feel that bad anymore? I don't feel that bad. And I think this is why when my client said, Bill, Google sets this number, we don't touch it, everything's fine. I could see that if these services aren't under heavy load, then that service is getting more than enough time to execute. Okay, fine. So we're not necessarily afraid of the latency on the 25 milliseconds, which is really nice because then what that means is that I could technically run 4 services on this single node at 250, and I don't have to buy, hopefully, any more compute than that if it's fast enough. If it's not fast enough, then I might have to give a service more time. The mistake a lot of people make with that is they've got a service calling another service, and they load this service with CPU cycles, and they don't do it here, and now this is throttling this. This stuff is hard. That's why I hate ops. It's not enough to say, you're not fast enough, give it more CPU. Yeah, but your auth service doesn't have more CPU, so it doesn't matter. Give it all day, it's slowing it down. Everything is working together. I've made that mistake before. Like, why is this not going? Oh, that's why, it's throttling it. Okay. So we have a general idea of what this number means. And things can get more difficult as we get more CPU. There's a couple of ways you can start to think about this. Whichever one works for you, you go for it. We could now say that I've got 2 CPUs. They each have a 100 millisecond time cycle. And so I could now give one service an entire CPU, say 1,000 M, and then maybe give 2 more 500. There's no CPU affinity. All we're saying is that you get a guarantee of 100 milliseconds of time every 100 milliseconds if you need it. There's still operating systems, right? Time slices going on and all that. But I could now say that a service can get 1,500 M, which would mean 100% of one time cycle and half of the other. Again, there's no CPU affinity. So the more CPU you have, right? The more you get to play that game. But if I only give my service 250 M or 25 milliseconds per time cycle, how many CPUs at any given time is my program technically using on this math? We would say 1. I mean, that's all it's ever really going to be using. Okay, let's just stay there for a second. So how does this affect sort of what we're doing in Go? To answer that question, we've got to understand how the Go scheduler works semantically. And then we've got to understand a couple more things. So let's talk about the Go scheduler. When your Go program starts up, currently in Go 1.24, the runtime will ask the machine, virtual or otherwise, how many cores are available to me. On this machine, the answer is going to be 12. And so the Go runtime is going to create 12 of these Ps, which stands for a logical processor. It's going to create an actual operating system thread. We'll call that M for machine. It's going to connect that operating system thread to the P. And then each P is going to be giving a run queue. We'll call this a local run queue. There will be a global run queue as well. I think the limit is like 512 Go routines per. It's either 256 or 512. I never look it up. It's one of those two numbers. But it's finite is what's important. And then I will have 12 of these. Let me for now just draw 2. Oops. Let me for now draw 2. But I will have 12 of these. And since the program is just starting up, I'll get a Go routine. It will be running, let's say, on this first P. And if that Go routine decides to create more Go routines, those Go routines can end up in any of the local run queues on any given P. Now, we still depend on the operating system to schedule that operating system thread on a core. And since I only have 12 cores, I only have 12 Ps and 12 Ms, it all works out great. What is a context switch? Let's talk about operating system threads for a second. What's really cool about Go routines is you can think of them as application level threads. The M is an operating system level thread. The semantics are actually the same for both. An operating system thread can be basically in one of 3 states. It could be running, it's on the core, runnable, it's waiting, runnable, it wants time on that core, or it's waiting, nobody even cares about it. Go routines have the same states. Operating system threads have stacks, so does Go. The semantics are really the same. The only semantic that a Go routine does not have is priority. And that's because Go routines are doing application level work. They're not handling events. We don't need to worry about the clock being updated. We don't need about a network packet. I don't need to worry about you touching the mouse. If we did, we'd have priorities. One of the bad things young Bill would do when we hired a new developer and they left their machine alone is we'd run a little program on it that downgraded the thread for the mouse from high priority to low priority. And we'd sit back. And they'd come back to their desk. And they'd move the mouse and nothing would happen. And they'd go, "Damn it, Windows!" And they'd reboot. And we'd all laugh. Or in the 90s, I'd walk into a data center where the servers were like single core 486 machines. and somebody would leave a mouse on that machine. And I would just do this for like 20 minutes while I was talking to somebody. I'd be moving the mouse. And like, I'm stealing CPU now, right? Because the operating system has to handle that event. It's got to context switch the thread off the core. I always wanted to build a little robot arm that I could just leave there. I said, this is what you get for keeping a mouse on a server, man. So we don't have events in Go routines. We don't need them. We're not handling events. But the semantics are still the same. In fact, it's a big crowd, so I'm going to ask this question rhetorically, but does anybody, keep it to yourself, know how long it takes for a context switch to happen in Linux at the hardware level? On average, that's about 1,000 nanoseconds or 1 microsecond. 1 microsecond or 1,000 nanoseconds essentially represents what? 12,000 instructions. Technically, every time a context switch happens with your operating system thread to that core, you're losing 12,000 instructions. I already told you 1,200 was a lot. I mean, that's massive, isn't it? The few people that have measured a Go routine context, it's come to about 200 nanoseconds or 2,400 instructions lost. Where would you like to context switch? Obviously. Okay. We're still dependent on the operating system to do its scheduling of that M to the core. But since we're using so less M's, right, just 1 M per core, right, we have a lot more opportunity for that M to be on a core at any given time. Obviously, the operating system needs those cores, and the more you run on there, the more noise there will be. But thanks to quotas, we could really minimize the demand for a given core at any given time. This is also a work stealing scheduler. The idea is that if this local run queue is empty, let's not make the M go into a waiting state or go to sleep. Let it go find work. Go look in the global run queue. Go steal some Go routines from another P. Why not? If we keep the M busy, it will stay on the core. Pretty cool. And so all of these things semantically are happening behind the scenes as Go routines are getting created and scheduled to execute and all of that. And in my case, I've got 12 of these going on. Now, the next thing that we have to understand, we've got a basic understanding now of how the Go scheduler is working. There's another really important component to this. You have to understand if you're going to be writing multi-threaded code, whether that's with operating system threads or Go routines. You have to understand the type of work you are doing. There are 2 types of work your program could be doing at any given time. One type is called CPU bound. The other type is called I/O bound. Now, just so we can get a couple of words defined before we continue there, the 2 big buzzwords, concurrency and parallelism. Let me give you the definitions that I'm going to use, at least in this talk. Parallelism means that we've got at least 2 threads, 2 or more threads, executing instructions at the same time because we have cores that will allow them to run at the same time. You cannot have parallelism unless you've got the hardware for it. Think of a thread as a path of execution. A set of instructions need to be executed, and that thread's job is to make sure they execute one after the other. If I have 2 cores, then I can have 2 threads executing in parallel. If I have 12 cores, I can have 12 threads running in parallel. If I have 1 core, there is no parallelism at all. What does concurrency mean? Concurrency means one thing: undefined, out-of-order execution. Get rid of all of your other fancy definitions and dishwashing scenarios. Throw them out. It's just that. Undefined, out-of-order execution. Now, I'm saying undefined for a really important reason. Answer this for yourself. But does anybody know what the Go spec says about map iteration? What does the Go spec, if you were going to write your own version of the Go compiler, and there's at least 6 of them right now, and you had to follow the spec, and it's now time to deal with map iteration, do you know what the spec says? The spec actually says nothing. It is undefined. The Go team has chosen to use a random algorithm once the size of the map gets to a certain size. So most people will say, well, it's random. It's implemented that way, but the spec, it's undefined, which means if the Go team decided to be evil in the next release of Go, it could switch out this random algorithm, still be compliant on the backwards compatibility promise. You couldn't scream at them, but how many Go programs are going to break? There'll be quite a few. So that's what I mean by undefined. The order of execution is not defined. It's not defined by a scheduler. It's not defined. There may be an implementation defined for one version on one operating system on one machine, but you can't count on it. Out of order execution, given a set of instructions, it doesn't matter what order we execute them in. As long as we execute all of them, we get the same answer. You can only use concurrency when you can leverage out-of-order execution. So as an example, if we were going to use a sorting algorithm called bubble sort, we can't do that concurrently. Bubble sort requires you to perform linear, traversals over and over and over again until something is sorted. There's no way to break that up and sort that out of order. Quick sort is an algorithm that can be done concurrently, and that's what the Go team uses in the sorting packages that are there. So that's concurrency. And now you know parallelism. Now, let's get back to CPU-bound and I/O-bound problems. A CPU-bound problem is one where getting rid of the noise, if that thread is given 10 milliseconds or 25 milliseconds to run, and it has work to do, it will use its full time slice every time because there's no reason for it not to. Now again, I promise, I understand that operating systems can choose a thread at any given time. This is not a real-time operating system we're running. Your CPU-bound thread might be chosen for the next clock update. Throw that all away because it's irrelevant. That noise sort of, it normalizes itself. So it never affects the behavior we're going to see. So don't go down that rabbit hole. Just understand the one thing. If we're doing something that is CPU-bound, then it will use its full time slice every time if it has work to do. So an example of CPU-bound work would be sorting, calculating Fibonacci numbers, calculating pi. There's nothing in the scope of that math that would stop it. Now, IO bound is different. The chance of that thread using its full time slice is really, really rare because probably less than 1 millisecond in, it's going to go hit the database. It's going to go hit that website. And that network call is going to cause the thread to now move from a running state back to a waiting state until the system call says, I'm done, and then it can move back into a runnable state, and then you're back into a running state, right? And so when we deal with IO-bound problems, we're rarely, if at all, going to use a full time slice of time. Something's going to stop us. Now let's play out some scenarios with IO-bound, CPU-bound, concurrency, and parallelism. Okay, let's imagine a CPU-bound problem. I've got 100 million, if I can spell it, integers. And let's say I'm going to use an algorithm where algorithm A is going to use one thread to do all of this work. I'm going to do an algorithm here. Let's also suggest that we have one CPU right now to work with. And then I'm going to write an algorithm that is concurrent. We're going to use 4 threads to do the sorting. Not important how that algorithm functionally works, just that we're going to use 4 threads and that we can do the work concurrently. So here's the question. CPU bound, one CPU. I can do this with 1 thread. I can do this with 4. Which one's going to be faster? In this particular case, the single-threaded algorithm is going to be faster. Why? Because at some point, these threads are going to cause context switches, and we're going to lose 12,000 instructions randomly. I can't tell you how many, but each run it's going to be different. But every time the context switch happens, that's 12,000 instructions we're not using to sort, we're using to put another thread on the core. So the more cores we have, the more threads we have, the more things we have to do, the worse that performance is going to show. The problem is that when a lot of you play with these types of things at your desk, you're doing very small numbers on very small systems, and you don't see the real difference. Then you put this stuff on like a big system, and you're like, why is this not performing? Okay, but what if I change this to be a 2 CPU machine? Now which one is faster? Well, the 4-threaded algorithm now should be faster because at least 2 threads can run in parallel at the same time. There's still context switches happening, but I'm getting a lot more work done thanks to parallelism. But I don't care about fast. I want the fastest. Well, if I'm going to use 4 threads, then I need at least 4 cores so I can eliminate the context switches. So here's the conclusion on CPU bound. If you have a CPU bound problem that can be done concurrently, you never want to use more threads than you have cores because you need parallelism to get to your highest efficiency. You want to eliminate the context switch. I love CPU-bound workloads. They're so simple to reason. It's concurrent, it's CPU-bound. How many cores do I have? That's all I need to know. The problem is none of us get to work on CPU-bound problems. I wish we did. We don't have that luxury. We all work on IO-bound problems. Let's go back. Instead of 100 million ints, It's now 100 million URLs. This can be done concurrently. Doesn't matter which URL, let's say, we pick up. Single CPU machine. Which algorithm is going to be faster? 4. Because now the context switches are helping us. We love context switches. Because the first thread gets, let's say if we're even this lucky, 1 millisecond in, it makes the call, context switch, put the next thread on, it stops, take it off, it stops. You see, the 12,000 instruction hit is saving us because we're able to get the next thread on, because that one that's going into a waiting state anyway. But you know me, it's not just about faster, it's the fastest. How many threads will allow this to run the fastest? Nobody knows. This is super complicated. And by the way, it changes throughout the day depending on which APIs are being hit. And so when you're at the operating system level for this stuff, this is why you need thread pooling technology. You can't just throw an operating system thread at every request. The scheduler will just die. So you need a thread pool. But what should the size of the thread pool be? Good luck. You do your best to run load and hopefully distributed load, right? Like not just the same API call, but maybe you can capture traffic using a technology like ngrok for a day. You get something, okay, so at noon, this is what our API calls look like, and we run that through and we try to tweak what should the thread pool sort of be. Now here's something that's interesting, because I worked on Windows NT and Windows operating systems until 2013 when I switched to Go. And their thread pool technology is called IOCP. The magic number for me was 3 threads per core. That's how I would set up the thread pools. And that always gave me a very good average sort of performance that was going on. Now, if you're a .NET developer, then you know that you have a single thread pool for every .NET program, which uses IOCP underneath. And Microsoft puts 1,000 threads min, 2,000 threads max, and it tries to figure out what that concurrency value is over time. And I've heard it's gotten pretty good by .NET 4. We don't have that in Linux and on the Mac or anything. So IO-bound problems are really hard to make efficient, because that thread pool is really hard to figure out. You might have moments where life is great. In other words, if you want to make sure that it's super efficient, you can't have more threads in the pool than you have cores in a running state. So if I have 4 cores, 4 threads in the pool can be running, 4 threads can be runnable, waiting, and everything else has to disappear. Because the moment you have 5 threads in a runnable state, you have the contention again. See what's going on there, right? We need that efficiency. It's impossible. It's impossible. Okay. But one of the nice things that Go did is said, don't worry about thread pools. And I would argue that you should never use a thread pool to try to gain some better CPU performance. You're actually probably, in those scenarios, going to cause the garbage collector to overpace because you've allowed it to be a little too efficient on memory. This is why in Go, it's better to throw 1 million Go routines at the problem and let this architecture, which is essentially like thread pools, take the Go routines and execute them all, and let the scheduler worry about the efficiency at a 2400 instruction context switch. Let it figure that out for you. This was the most beautiful thing I'd ever seen coming from Windows. I didn't have to worry about a thread pool anymore. I could just give it to the scheduler and it will find, yeah, Bill. The only reason you would ever use a thread pool now is because you have a resource management problem. You can't throw a million Go routines because each Go routine has to get a file handle or has to get a connection. Now you might need a pool. But we avoid that. Okay, so let me sum up what's going on here. You understand now, CPU bound, beautiful. What's the maximum efficiency? Well, we have to use parallelism, and we never use more threads than we have cores. I/O bound, Now I want to show you the real beauty of the Go scheduler. Come back to this for a second. I'm going to draw a line right here. I'm going to draw I can't draw it any thicker because I don't have my toolbox. But I'm going to draw a line right here. Everything up here is at the OS level. Everything down here is at the Go level. Or we could say your app level. I want you to see something that's really magical. What the Go scheduler has done is that it has converted. It has converted I/O-bound workloads into CPU-bound workloads. Think about it. The Go scheduler has made every single Go program on the planet a CPU-bound program. How many M's do we create? I don't know, Bill. How many cores do you have? That's CPU-bound. We try to keep those M's as busy as possible so they don't come off. That's CPU-bound. Think about it. When a Go routine is being context switched off the M, and another Go routine is coming on the M, that's a context switch at the app layer, but from the operating system's point of view, that M is still just busy executing what? Instructions. This is why Go programs are so fast. This is why you want to throw a million Go routines at it. Because what you really have in front of you, for the first time, all of you can say that I am a CPU-bound programmer. Because everything I do runs in a CPU-bound mode. Now, if you're dealing with blocking system calls, it gets a tiny bit muddy, but we're not doing that. We're working with networking. And all networking calls in Go are asynchronous system calls. And so this just hums. Now, this conclusion is important because I'm going to tie it back now to the Kubernetes side. But we all now know that every Go program is a CPU-bound program. And we know to execute at your maximum efficiency when you are CPU-bound, you never want to use more threads than you have cores. Now, if I come back here, I'm going to run some load in this system. It's just 1,000 requests, a small number, using 100 concurrent connections. I'm going to run it twice because I never trust the first time. Even when I run tests that are like benchmarks, I always run it twice. Okay, so currently right now, this program is set at 250 M, 25% of a CPU. It's running at 133 requests per second. We see these other numbers as well. Let me bring up, come on. Let me bring up just a regular notepad for a minute. Just put this in here. All right. Now, if I ask for, let's say, the logs here. Let's see if I can, I won't be able to get to the logs. So I might have a liveness endpoint here. In my liveness endpoint, right now, this service, was told that you have 12 cores, and so the Go program created 12 threads. However, I set a quota of 250M. I told Kubernetes, only give this Go program essentially 25% of a single CPU at any given time. I'm using 12 threads. I am CPU bound, but I'm really just using one core. How many threads should I be using? I should be using one if I'm a CPU bound program. This is really scary right now because this is what's happening. I've been given 25 milliseconds for every 100. But that time is added up for all the threads that are running in your process at that point. So how quickly is 12 threads, if they're all running at the same time, going to eat up that 25 milliseconds? Almost instantly. I'm really not getting any work done because I got 12 threads eating up 25 milliseconds like this, stopping, then they get to go again and stop. And even with that, I'm running at 133 requests. You saw the numbers. Now, if everything I said is right, since this is CPU bound, if I run this Go service as a single threaded Go program, it should run faster. It's weird. Wait, Bill, we're going to downgrade this Go program to run with a single thread, and it's going to run faster? Yeah. Now, how do we do that? There's two ways. There is a package published by Uber called something like MaxProx. I don't have internet. That's okay. Something like MaxProx. Essentially, you just import this package, and it tries to see if you're running in Kubernetes. And if you are, then it will readjust the Go MaxProx. And it's a good software solution for this. My problem with that package is I've seen it not work in certain containerized environments. Your next option is to just change a little YAML. So what I'm going to do is in my base YAML here, if I can find it, I'm going to add this. Now what that's going to do is tell Kubernetes to set the Go MaxProx variable to match what the limits.cpu value is. But Bill, that's set to 250M. Okay, but Kubernetes changes that to 0.25, and then they use a math ceiling function when they write this variable out, and they make it 1. And if it was 1500M, well, that would be 1.5, and math ceiling brings it to 2. So this is an ops solution. Okay, so I'm going to save this. I'm going to come back here. I'm going to reapply that YAML. Got to wait for the pod to reset. It's doing that now. Once that's done, we can quickly look at the logs. Actually, I can use the liveness again. I'm just waiting, 2 for 2. I've hit my liveness endpoint, which is what I always use for extra information. It now says 1, right? All right. Let's see if I'm a liar. We're going to run it twice. I'm even going to let you look at that one. There you go. By the way, you should be freaking out because I only sent 1,000 requests through the server, and we've almost doubled the performance. This number is so small that I'm doing on load, and that number in comparison is gigantic. Now, this is why I said when I started, I believe there's a lot of Go services running in Kubernetes that are not running as efficiently as they otherwise could when you're using quotas and you don't match the quota to the number of threads, because at the end of the day, Go programs are really CPU bound. This proves it. If you're not using quotas, that's a whole nother conversation. I'm not getting into the ops thingy at all. But you do need to validate and check these things. Pretty cool. I'm out of time. So I hope you guys all enjoyed that. You can come and ask me questions later.
Oh. Thank you, Bill. It was truly inspiring, or a gift to help. Thanks.
I got to get this through customs now.
Thank you, Bill.